Hi everyone, Big Mac here. I haven't done a math video in a while, so I figured I would kind of cop out and just use something that I actually wrote as part of my algebra class that I've been teaching. This was an optional lecture, or a bit of notes I gave on them. It talks about the rule of signs and the rational root theorem. So lately, just to give a brief summary, we've been discussing some different techniques of solving when polynomials cross the x-axis in a traditional graph. So obviously we can look at, certain factors of it, try and see where it crosses just using the graph, and try and get some ideas on whether or not our roots are going to have single, multiplicity, or possible double, triple, just by looking at different properties of the way the graph looks and stuff like that. So I got a few things here. I'll just cut to the chase of it really quickly for the most part, because I could read all this stuff to you guys, but there's really no point in that. So basically, what we want to do is we want to try and find a different technique for finding our possible ideas of where our roots are going to be of this polynomial, where it's going to cross the x-axis. So, obviously if we don't have our calculator, that's going to make things a lot more complicated. However, there are a couple of older techniques, old school I guess you could call them, that enable us to try and at least get an idea on where these solutions might exist. Again, they're not foolproof, but they can come in handy in a clutch. So the first one I wanted to talk about was the rule of signs. This might actually be attributed to Descartes, I believe, in some books. But basically, what we want to do is we want to track the coefficients in our polynomial f of x. Whenever those coefficients switch from positive to negative, or vice versa, from negative to positive, we want to keep count of that. So we want to count how many times that happens over our polynomial, and that's going to give us an idea on how many roots we can have on either the positive or the negative x-axis. So like our rule here is, for positive numbers, see how many positive zeros of our function we have, look for the number of sign changes in f of x. And then we're going to have to account for possible complex values, so it might be minus some multiples of 2. Likewise, if we want to get an idea on how many negative zeros we have of our function, we need to check the number of sign changes in f of minus x, where again these are just our polynomial values. So like I mentioned, the multiples of 2 part, that's just because there are possible complex roots, and if you know anything about those, you know that they come in complex conjugates, so they account for roots 2 at a time basically. So that's where we get this minus multiples of 2 situation. So here we have one example. We have x to the 5th minus 13x squared minus 12x plus 2. So we just wanted to gauge an idea of where these solutions may or may not be. So looking at the rule of signs, going back to how many positive solutions we can try and find, we need to see where the coefficients change place. So we have it happen twice in this case. The first case is here from 1x to the 5th to minus 13x squared. Don't include zeros when you guys are when you count these things. Zeros just kind of make things complicated. But so we had our first one here where the coefficients change from 1 to minus 13, and we had another switch. Here it stays positive from minus 13 to minus 12, but we had a second switch here from minus 12 to positive 2. So we had 2 total sign changes in our positive f of x, which, accounting for, again, possible complex solutions, means that we will either have 2 or 0 positive solutions. Doing a little bit of quick algebra on our negative f of x function right here. Basically, we plugged minus x into our polynomial and see what got spat back out. We notice that our coefficients changed, and now we only have one sign change. Here from negative 13 to positive 12. Over here it stayed negative, and over here it stayed positive, so we don't care about those. So there was only one instance where the sign actually switched from positive to negative, or negative to positive in this case. So what that tells us is that we can be certain that there is at least, or in fact there is only one negative zero, or solution in this case. And that is a true thing. Whenever there's an odd number, we can expect at least one. So that's a useful thing. So we can get an idea on where these solutions are, but what are they exactly? So, often when we try and solve these things, and our calculators are going to spit out all of our, irrational solutions as just long decimal approximations. But what about the nice numbers? Is there any way to find either our quote-unquote nice solutions? I'm making air quotes even though nobody is seeing this. Whatever. Anyway, so the other possibility is to use the rational root theorem, where basically we're going to look at our coefficients and try and derive from that where some possible solutions might be. So again, for this case, I'm going to write our polynomial in a long form, where we have a sub n is the leading coefficient, the term in front of the x to the n power, and a sub 0 is just going to be our constant term. Just the coefficient at the end. So what our fractional root theorem tells us is that if there is a fractional root, again, there's absolutely no guarantee that there has to be, but if there is one, it tells us that it has to have to do with the factors of both the leading term, the a sub n, and the constant term a sub 0. So in fact, it does have to be in this form, plus or minus, because, we can't really be sure. A over b, where a is going to be a factor of the constant term and b a factor of the leading coefficient. And by factor, I just mean your basic divisors, nice even divisors of a number. So for example, the factors of 18 are 1, 2, 3, 6, 9, 18, stuff like that. So obviously this is going to give us potentially a very large list of candidates. However, if there are any roots or any fractional roots to this equation, they have to be in this list. So even though we might get a lot of, trying to think of a good word for them, false positives, we can be sure that at least if there is one, it has to be a member of this list. So going back to that earlier example where we had x to the 5th minus 13x squared plus 12x plus 2, we can work at the same vein. So we can see that the factors of the constant term are just 1 or 2, and if in this case the leading coefficient is just 1. So what that tells us in terms of possible candidates for our rational function, or possible rational zeros, we only have 4 possibilities. So we have minus 2, minus 1, positive 1, and positive 2. So if there are different techniques to evaluate whether or not these functions are solutions. Either plug them in, see if they cross the graph at that point, different techniques. So it turns out one of them, minus 1 in this case, yes, minus 1 turns out to be the root in this case. So knowing what we know about relating roots to the factor of a polynomial, we now know that x plus 1 is a factor of this polynomial, and when we factor it out, we get this nasty looking thing, x to the 4th plus ... plus 2. We can repeat this process again, try and get an idea on where positive or negative roots might be, as well as get an idea on what possible rational roots there are. Unfortunately, in this case, we've pretty much run out of options. It does turn out that even though it's a 4th order polynomial, there are 2 real positive solutions. Unfortunately, they're both nasty irrational numbers, and then we also have 2 complex roots in this case. So let's look at our second example here. We have 2x cubed minus x squared minus 16x plus 15. Little quick work on my part here. Let's just open up some notepad. Yay. Notepad. So we'll have our equation here. It was actually minus 16x up here, my bad. Factors of the constant term, 15 is 3 times 5, 1 times 15, so we have possibilities of 1, 3, 5, and 15. For our leading term this time, we have 2 in the coefficient, so either 1 or 2 is a possible factor of that. Looking at the number of sign changes, we can quickly see that for our original function, we have one change here from 2 to minus 1, and another one from minus 16 to positive 15. So we have 2 sign changes, which means that we will have 2 positive roots, or 0 because of, complex conjugates and stuff. Doing the same thing for f of negative x, this will be minus 2x cubed minus x squared plus 16x plus 15. So noticing that we have 1 sign change here from minus to positive, again when we evaluate this through f of minus x. So that does guarantee us that there is 1 0 that is negative. Again, whether or not it's a rational function or an irrational number, we don't know. But knowing what we have about our factors, we can generate a list of possible rational zeros. So here we have them down here. We have, again, just take a fraction or one factor of the constant term and divide it by a factor of the leading term. Yeah, the leading coefficient. So again, you can have multiple possibilities and then plus or minus as well. So in this case, it looks like we have 16 solid possibilities. A little bit of sleuthing. Just granted, a lot of guess and check on my part also. It turns out that 5/2 is a 0 for this function. I just did some really quick synthetic division on this part. It looks right. Anyway, so we know that our remainder is 0, so that tells us that 5/2 is a solution to our polynomial. And if you guys want to know how to do synthetic division versus traditional polynomial division, there are videos on that online. I'll try and link you guys to a good one that I find. So in terms of our remaining factor, we now have that our 2x squared, or that our polynomial, we now know that since 5/2 was a factor, we can pull out a factor of x minus 5/2. Through our synthetic division, we see that our coefficients for our remaining polynomial are now going to be 2x squared plus 4x minus 6. Obviously, we can factor out a 2 from all these terms on the right side, and then I'll combine that back into the x minus 5/2 term, so we'll have 2x minus 5. The other useful thing to notice is once we factor out that 2, x squared plus 2x minus 3 is all that remains, and that is a lot simpler polynomial to factor out, just x plus 3 and x minus 1. So in short, what that tells us is, whoops, wrong button. Come on. Scroll up a little bit. There we go. So what that tells us is that in this case we had 3 zeros. So we had 5/2, minus 3, and positive 1. Again, this is exactly what we predicted using the rational roots theorem. We predicted that there were going to be either 2 or 0 positive values and 1 negative value. So indeed, here we found 2 positive solutions and 1 negative solution. So this is just something useful that, you know, if you want to get some work in algebra, send me any comments, questions if you guys have them. Otherwise, this is Big Mac saying later.